Welcome back, everyone. This next section is section 6.2, solids of rotation or rotational volume. The key thing today we're going to talk about is volume. Okay, this is one of two different ways to calculate volume. If you don't know anything about area, check out the last video. You cannot do this section on volume unless you understand the last section on area. So let's take a look at this. Suppose I start with this curve, y equals the square root of x. My boss at the Acme Rocket Company has assigned me to build a nose cone in this shape. So I put a piece of wood in a lathe and turn it to shape to match the cone. So what shape is this going to be? Well, it's going to look like this. Okay? So I'm going to have a 3D shape. It's round with a curve for the front. Kind of looks like an acorn or something like that. That's supposed to be the nose of a rocket. How do I find the volume of that cone? One way would be to cut it into a series of thin slices and add their volumes. Just like we did with area, we did top minus bottom, and we found that. What shape is this tiny little shape? Well, it's a rectangle. But if I were to rotate this rectangle around this way, it wouldn't be a little rectangle anymore. It would make a little cylinder. Well, what's the volume of a cylinder? It's pi r squared h. Oops, h, not pi again. Well, let's figure out what some of this stuff is. Pi is always pi. The radius is the function. And h, how tall is it? Well, it's as tall as this is. But I want it to be really, 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 really small. So I'm going to put a dx in here. That shows me that I'm using a really small cylinder. And the r value is the case of the function. In this case, the square root of x. But it could be any function. So that's for one cylinder. One tiny little disc is what we call these things. So how do I put them all together? Because I need a disc here, and here, and here, and here, and here, and here. And I want them to be infinitely small, which means I need an infinite number of them. What do I use in calculus to find the sum of an infinite number of infinitely small areas or volumes? What do I use? I use an integral. So, let's talk about this. And I actually like to write it like this, with the pi on the outside, because pi is just a number. Where did the 0 to 4 come from? They came from the starting point and the x value of the ending point. I'm sorry, 4 comma 2. This is 4, 2. So those are the bounds. Why do I use dx? Because I'm rotating it this way around the x-axis or parallel to the x-axis, so I have to use dx. What's the radius in this problem? The radius is the function. It's the square root of x squared. Now it's a simple problem. This is x. That makes 1/2 x squared, evaluated from 0 to 4, which makes 16, half of 16 is 8 pi. The volume of that shape is 8 pi. So again, let's talk through this again. It's pi because I'm rotating. It's an integral because it's a sum of an infinite number of cylinders. 0 to 4 is where I'm going from and to, the x values. I use x values in dx because I'm going this way, so I need a right and a left side, a left and a right side, backwards. And it's the function, the radius, squared. So, what's the general idea for the disk method? Pi integral radius squared dx. Why do I have a pi dy? What's this over here represent? Why do I need two different functions? Well, in this last example, we rotated this way, parallel to the x-axis, which means you have a left and a right side. But I can rotate this way, parallel to the y-axis. And now I don't have a left and right side. I have a bottom and I have a top. If I have a bottom and a top, these aren't x values anymore. These are y values. If If I use y values for my bounds, I need y values for everything, so it's dy. You'd have to rewrite the problem. What about something that looks like this, where there's an outer function, x squared, and there's an inner function, 2x. We're going to treat this very similar to the way we did area. Area was big minus small, or top minus bottom, or right minus left, however you want to think of it. Volume is going to be pi times the big one squared minus pi times the small one squared. Or if you use a little bit of algebra, I can factor the pi out, and that leaves me the big one squared minus the small one squared. But if I want to do an infinite number of these areas, I'm going to have to do the integral. Now on this picture, since I'm rotating this way, is this going to be a dx or a dy problem? It's dy because there's a bottom and there's a top. So I know that whatever I do is going to be dy. So I'm not going to use y equals x squared. I'm going to use x equals square root of y. And I'm not going to use y equals 2x. I'm going to use x equals 1/2 y. So my big function is the square root of y squared minus my little function is 1/2 y, or y over 2 squared. Now, I'm going to use the calculator to do this because we've done enough integral problems. I trust that you can do it. Okay? So let's plug that in exactly like we see it. And again, I'm not going to plug the pi in. So it is, I don't have a y button, so I have to use x. And the square root of x squared is just x minus parentheses x divided by 2 quantity squared. Second trace 7. And my bounds were 0 to 4. So it's 2.66667 repeating, which is 8/3 pi, because I didn't include the pi in the answer. Even though it's y's, I can plug it in my calculator as x's. It doesn't have a y button. So, what's the formula if there's two functions? It's the top squared minus the bottom squared, or the big squared minus the small squared, d whatever. Depending on whether you're going this way, it makes it dx, and it's all x values, or this way, and it's dy, and it's all y values. Let's try a problem. Find the volume of the solid formed by revolving the region bounded by the graph. So I've got x cubed, which looks like this. I'm drawing these very roughly. You guys could use a calculator. Y equals 8, which looks like this. And x equals 0, which is this. So this is my region in here. Let's talk about some important points before I keep going. What point is this where they cross? That's 0, 0. What's this point? Well, I know the y value is 8. What number, if I plug in there, would give me 8? It's 2. And I want to go about the x-axis. So I want to go this way. If I'm rotating this way, is this a dx or a dy problem? It's got a left side and a right side. It's a dx problem. So that's the first thing I'm going to do. Is I'm going to write pi out front, and I'm going to put dx at the end. Just that'll tell me what's going on here. Now I'm going to go top minus bottom. What's the top function here? The top function here is y equals 8. So it's 8 squared minus, what's the bottom function? It's x cubed squared. Or if I clean that up, it would be pi times the integral of 64 minus x to the 6th dx. What am I forgetting? The bounds from 0 to 2, the x values. Not 0 to 8, those would be the y values. Integrating this, and I'm going to do this one by hand because it's pretty easy. 64x minus 1/7 x to the 7th. You evaluate it from 0 to 2. If you plug all that in your calculator, you get 768 over 7 pi. You can multiply the pi in if you want, and on some tests they will, on multiple choice tests they might. I like to leave the pi separate. So again, we're rotating this way, so it's dx. That means my bounds are x values, 0 and 2. The top function is 8 squared minus the bottom function is x cubed squared. Once you have it set up, it's just simple calculus from there down. What about a problem like this? Bounded by x squared, that's a parabola. X equals 2, that's a vertical line. And y equals 0, that's a horizontal line. So I'm talking about this little area in here, that little triangle, rotated about the y-axis. Ooh, something a little bit different. I'm going this way now. I have a bottom and a top. That means I need a dy. So let's set up this problem. Pi has a dy at the end. That tells me everything has to be y values. Let's talk about the bounds. This side is 0, 0. That's the easy point. This side, if the x value is 2, what's the y value going to be? 4. So my points are 0, 0, and 2, 4. I need the y bounds, so I need 0 to 4. Now let's talk about far and close, and remember they have to be y values. They have to be x equals something with a y. From this axis, which of these two functions is further away? The line is further away from the axis. The line is 2. Which one's closest? X squared is closest. X squared is the small function, but I can't put x squared in here. I need to do it in y's. So that's square root of y squared. And that's the setup for the problem. Easy problem to integrate. That's pi times, that's 4, and if you integrate 4, you get 4x, minus, that's y, so that'd be 1/2 y squared. I don't know why I put x, it should be y, I'm sorry, 4y. Evaluated from 0 to 4. Plugging in 0 gives you nothing, so I don't have to worry about it. If you plug in 4, you get 16 minus 8, which is 8 pi. So the volume of that shape when you rotate it is 8 pi. Why did I use dy? Because I'm rotating around a y-axis or something parallel to the y-axis. So far we've done a problem with the x-axis and with the y-axis. But we can rotate these around things besides just the x-axis and just the y-axis. Take a look at this problem. Now instead of going around the x-axis, I'm going to go around x equals 2. So it's still going this way, and it's still a dy problem. But now I've got to consider the fact that I'm not going around the axis, which is the number 0. Here's your new formula. Axis minus top squared minus axis minus bottom squared. So it's the same thing, except I have to put axis minus in front of each thing. Or axis minus big squared minus axis minus small squared. What do I mean by that? Let's try a problem. Square root of y, square root of x. X equals 0, y equals 2. Again, drawn very roughly. So this is the area in here. Okay? But now I want to rotate it over the line x equals 4. I'm rotating it over here. Before I get too far into this, let's figure out the points, the bounds. That's 0, 0, that one's easy. What about that point? Well, if y is 2, that makes x 4. So let's set this up. Pi. Well, let's ask this question. If I'm rotating it this way, is this a dx or a dy problem? It's got a bottom and a top, so it's going to be a dy problem. Which means I need to use the y values for bounds, 0 and 2. Now I have an axis that I have to consider. So it's going to be 4 minus, from this axis, which is the furthest function? The square root of x, or this function, which is 0? From the axis, the 0 is the furthest function. Axis minus the far one squared, minus, axis minus. I can't put the square root of x in this problem. Why not? Because it's dy. Square root of x is y squared, dy. I'm going to cheat this time and use the calculator. Half the test is calculator, so knowing how to use it's important. I'm going to plug in the integral just like I see it. I'm not going to overthink it. 4 minus 0 squared. I know that's 16, but I'm going to go ahead and plug it in like I see it. Minus 4 minus, I don't have a y button, so I have to use x squared, squared. Second trace 7. From 0 to 2. And it tells me it's 14.93 repeating. And if you plug that in your calculator, you find out that 14.93 repeating is 224 over 15 pi. So that's my volume if I rotate that shape. Again, it's dy because it's this way. It's got a bottom and a top. That does it for rotational volume. There's one more section on cross-section volume that we're going to do next. It's the last section of the year. That's good. If you have any questions with this, come talk to me. Come see me. Thanks, everyone.